Hello there, Mr. Sutton here with the AB Calculus 5-6 Extra Practice Number 1 solutions on trapezoidal rule. For this problem, they want us to approximate the area under this curve using the trapezoidal rule with 5 subintervals. So we're going to start by making a table. So my x values, since I have a distance of 5 from one end of this interval to the other, my subintervals are going to have to go by ones. So I'm starting with the x value -2, that's my leftmost endpoint. And we have a trapezoid from -2 to -1, and then to 0, 1, 2, and 3. All right, now we're going to come up with the y values to go with these x values. So we have heights of the trapezoid that we can average together. So I'm going to just get these using a table on my grapher. So I'll begin by putting my f of x in y1, and then let me just go to second window and set my table up. So I'll be starting at -2 for this one, going up by increments of 1, and then I'll just go to second graph to pull up that table. So we've got 7, 10, 11, 10, 7, and 2. Let me just put all of those in there. This is just straight out of the table from my grapher. All right, now let's go ahead and use our trapezoidal rule. So we can say that the integral from -2 to 3 of f of x is approximately equal to the following. So my first trapezoid, I'm going to have 7 plus 10 over 2 times an interval length of 1. Next, we have a base of 10 plus a base of 11 over 2 times a height of 1 again. These all have heights of 1 for these trapezoids. Then we've got 11 plus 10 over 2 times 1, 10 plus 7 over 2 times 1, and 7 plus 2 over 2 times 1. And you could leave it like this, unsimplified, or you can plug it in the calculator. I'm going to do that now. To do this a little more efficiently, since I noticed that all of these trapezoidal areas are dividing by 2 and multiplying by 1, I'm going to just open up a parentheses here. So I'm going to do actually alpha y equals and then do n over d to get my fraction mode. I've got 1/2, and then I'm going to open a parentheses, and I'm just going to put all the things that are being added in the numerator in this parentheses. So we've got 7 plus 10, and the rest of these now. There we go, got my number lock on. 7 plus 10 plus another 10 plus 11, and you're going to add a bunch of these things twice. Plus 11 plus 10 plus 10 plus 7 plus 7 plus 2. Not so bad when you kind of have a pattern there. And that's going to be 85 over 2. Which if I wanted to, I could go to math and turn that into a decimal. Either way, 42.5, there it is. For this one, they want us to approximate this integral using the trapezoidal rule with the intervals given by this table, basically. So I can say that this stuff is approximately equal to, so for my first trapezoid, I've got 7 plus 3 over 2 times a height of 1. Next, I've got 3 plus -2, or 3 minus 2 over 2, times a height of, well, let's see, this is going to be 12. And then we have -2 plus -1 over 2, times a height of, well, from 13 to 22, that's going to be 9. Then we have -1 plus 0 over 2, times a height of 5. 0 plus -3 over 2, times a height of 3. And then finally, -3 plus -7 over 2, times a height of 9. And you could leave it unsimplified, or I'm just going to go ahead and plug this in my calculator. So there we go. I spent a while off camera plugging that in, and just pressing enter now at the conclusion of all this comes out to that number, which if I go to just my math mode and go to decimal, I can turn that into a decimal, -54.5. For this problem, we're given this function x squared times e to the -x, and they're giving us this fact that from 0 to 1, the integral of this function is this crazy decimal. If a midpoint Riemann sum with 2 intervals of equal length is used to approximate this, what's the absolute difference between that approximation and this integral? So basically, we have to figure out a midpoint Riemann sum total for this function, and then we have to compare that with this number right here and figure out how far apart they are. So I'm going to start by defining a constant m, and I'm going to set m equal to the value of this midpoint Riemann sum, and I'm going to do that on my calculator. But to get that, I basically need to figure out my midpoint plug-in values and use those along with the heights at those values to get some rectangles. So let me just figure out how wide each of these rectangles should be. Since I'm using two intervals of equal length and I'm going from 0 to 1, that means each rectangle must be 0.5 for the base. And then for the height, I'm just going to plug the midpoint x value into the function. So for my first rectangle, and now I'm computing this m that I just talked about. This is the midpoint Riemann sum value here that I'm going to store on my calculator. So this is going to be my base of 0.5 times a height of, well, whatever I get when I plug 0.25, the midpoint value, into the function. And for my next rectangle, I've got a base of 0.5 times a height of, well, now that the next x value between 0.5 and 1 is going to be 0.75, so I need to do 0.5 times f of 0.75, and adding these things up is going to give me some decimal. Let me see what that is in my calculator. So, by the way, the first thing I've done is to actually enter this function into my y1 in my y equals. That'll make it easier to deal with. Now, quitting out of there, let's do 0.5, and I want to plug 0.25 into the function. So I'm going to do alpha trace, pull up y1 from there, and I'm plugging in 0.25. So this is going to give me that area of the first rectangle. Now I'm going to add to that basically 0.5 again times alpha trace y1 again, but now I'm plugging in 0.75 and close the parentheses. And now I want to store all of this as m. So to do that and to get the answer at the same time, I'm going to press the store button, and then let me do, let's see, alpha m right there. I mean, it doesn't really matter what letter, but m makes sense because this is a midpoint sum. So let me press enter there. And it comes out to about this number, 0.1572 and some change. Well, that's great. In fact, that's pretty close to choice D, and you might be tempted to pick that. But we're not there yet. We need to figure out the absolute difference between this and this other value they gave us. Now, you could, if you wanted to, just use the value they gave you, subtract these, and come up with a number. And this will be accurate enough to give you any of these numbers. But if you want to get fancy, you can set it up like I did here. So I'm going to take the absolute value of this m minus the true integral value. I mean, I figure since I'm using the calculator anyway, why don't I just do this and get the exact value? So let me do, let's see, alpha window and pull up my absolute value here. And I'm going to do alpha m to get that back. And now from that, I'm going to subtract. Let me do math 9 and pull up my integral. I have an integral from 0 to 1. And in here, I'm going to be integrating this function. So let me go ahead and do alpha trace and pull up y1 and put it in there. And let me do dx here. And let's see what this comes out to. About 0.003. We just need to be accurate to 3 decimals. So that's going to give us choice A. For this neat problem, we have a definite integral from 0 to 4 of the square root of x, approximated with a left Riemann sum, a right Riemann sum, and a trapezoidal sum, each with 4 subintervals. So we've got L, R, and T to represent those different sums. We want to know what order we should put those sums in. So we have all 3 of those approximations plus the true value of the integral itself, and we're trying to figure out what order these go in. So this is all about knowing whether an approximation under or over approximates it and by how much. Now, normally, we just have to figure out if a left or a right Riemann sum under or over approximates something, and that's the end of it. But here we have to actually compare it with other things, including a trapezoidal rule. So it all depends on what kind of function we're dealing with. Then there's a few things we have to look at. For example, square root of x is an increasing function for across its whole domain from 0 to infinity. Because radical x increases, that means that LRAM is going to underestimate it, while RRAM overestimates it. So definitely, I mean, if nothing else, L should be to the left of R in our setup. So that's going to narrow it very quickly down to choices A and B. So just for knowing this much, you've already cut your answer choices in half. Now, we see in both these answer choices that the trapezoidal rule is between L and R. And it makes sense that the trapezoidal rule has to be between these, because trapezoidal rule in general is more accurate than either of these approximations. It's just a tighter fit because you're allowed to use trapezoids instead of rectangles. So since it's closer to the true answer, it's going to be between the underestimate and the overestimate. But is trapezoidal rule going to be greater than the true value or less than the true value? We still need to figure that out to choose between choices A and B. And for that, we have to look at the concavity of the curve, because that's what trapezoidal rule is all about when you're talking about under versus over. Radical x, this function here, is a concave down curve across its whole domain. Trapezoidal rule, therefore, is going to be underneath the curve at all points. So trapezoidal rule underestimates a concave down function like this one. So then, going from left to right, the smallest of all of these is going to be LRAM. That completely underestimates it. Trapezoidal rule kind of sort of a little bit underestimates it, so that one's next. Then you have the true value of the integral, which was being underestimated by these other two. And finally, that's going to be less than the overestimate, which was RRAM on this one. So our answer choice then is going to be B. On this calculator-based problem, we're given the function f of x equals cosine of radical x, and our first task is to approximate the integral from 1 to 3 of f of x using MRAM with these subintervals. So first off, I'm going to say integral from 1 to 3 of f of x is approximately equal to. If I don't write approximately equals here, then I'm going to lose a point right off the bat on this free response question, because I really need to understand the fact that this is an approximation. It is not the true value. All right, so now we have to set up some rectangle areas that we're adding together. These are all going to be base times height kind of setups. So on the first interval, the first subinterval, we have a base of, let's see here, from 1 to 1.6, that's a base of 0.6. And for the height, we have to take a number and plug it into the f function. But which number? Well, with midpoint Riemann sum, you have to take the x value exactly between the endpoints of your rectangle. So we're going to be using 1.3 for our plug-in value. So when all is said and done then, our first rectangle area is going to be 0.6, that was the base, times f of 1.3. For the next rectangle, we have a base now of 4 from 1.6 to 2, and we're multiplying that by f of 1.8, the x value that's halfway between 1.6 and 2. For this last interval, we have, this time it's a base length of 1 from 2 to 3, so that one's kind of nice. And our midpoint x value is 2.5 this time around, so we have 1 times f of 2.5. And I'm going to write all this out because this will at least give me some kind of credit for having the setup of the problem. To get the last point, though, I need to have some kind of truly numerical answer. Just writing f of 1.3 is not good enough. So let me just plug it all in the calculator and see what it comes out to now. To make my life a little bit easier, I'm just going to enter this function as my y1 so that I don't have to keep rewriting things. And then quitting out of there, let me do, let's see, 0.6 times, let me do alpha trace y1, and I'll plug 1.3 into that. 1.3, there we go. And then we're going to do plus, we need 0.4, alpha trace y1. Now I'm plugging in 1.8 plus alpha trace. Actually, before that, I guess we could go straight to the alpha trace. Let me just write 1, why not? And then alpha trace y1. Now we're plugging in 2.5. And pressing enter on that mess is going to give us approximately 0.331. For this problem part, now I want to approximate this integral using a trapezoidal sum. Still have the same subintervals that we used in part A, but now it's a different setup. So this is now going to be approximately equal to the following. And these are all going to be trapezoid areas. So I'm going to be doing a base 1 plus base 2 over 2 times the height. So in this one, the bases now with the trapezoid, those are actually the output values of your function. So I have to do f of 1 plus f of 1.6 all over 2 times a height now. The height takes the place of the rectangle base. It's a height of 0.6. Plus, for this next one, I've got f of 1.6 plus f of just f of 2 all over 2 times, now we have a height of 0.4. And for this last one, Our height's going to be 1 this time around. We have f of 2 plus f of 3 all over 2. Again, I need to plug this into the calculator. It's not enough to just write f of 1. I mean, what is f of 1? I need to put an actual number in here to get credit. So here we go. So again, just like with the first part here, I've got this f function in my y1, so I can refer to it fairly quickly. And now let me do, let's see here. Let me do alpha y equals to pull up my fancy fraction mode. I've got, this first one is going to be f of 1 plus f of 1.6 up top. So let me do alpha trace y1. We have f of 1 plus, let me see, alpha trace. This is going to be 1.6 that I'm plugging in now. And divide that by 2. And we're going to multiply all that by 0.6. And I'm going to do the rest of these off camera now. There we go. I've got it all set up. It's way faster off camera because I can use both hands. I'm not holding a mic with one of them. Here we go, pressing enter. It's about 0.342, which isn't too far off of our value in part A, so it's at least within the realm of reasonable here. For this problem part here, it is known that f prime of x equals this craziness, and f double prime of x equals, well, this is even more crazy. We want to know if a trapezoidal approximation for this, like the one we found in part B, would over or underestimate the true value, and give a reason. Okay, so there's a lot of ways to do this. I mean, you could actually, since it's a calculator problem, take the integral of this thing from 1 to 3 and see what happens and compare it to your answer. But that's not really a rigorous way of doing this. What they're really looking for here is for you to check out the concavity of the function and then use that to figure out if a trapezoidal sum over or underestimates. So to talk about the concavity of f of x, and we're talking about the concavity on the interval from 1 to 3 only, we just need to graph f double prime. So let me go ahead and do that real quick. So I'm going to take that back. There was nothing quick about entering this thing in the calculator, but we're here now. So I've entered it as y2. I'm going to deselect y1 because I don't want to graph the original. I just want to graph this f double prime, and I want to graph it on the interval from 1 to 3. All I really care about is, first off, does it cross the x-axis at all? And if not, is it above or below the x-axis? Because that's going to tell me the concavity of f. So let me go to Window, and again, we're going from 1 to 3 for this. And let me do zoom 0, zoom fit. And here we go. Put on your seatbelts. This is a wild ride through concavity land here. So it looks like, is it going to cross? Is it going to cross? It's getting closer. It's getting closer. And at the very end, it touches, but we just need it to be consistently one way or another on the open interval. So we can see here that, well, where is the x-axis? That's a great question. Let me see what my window is. So my window, I'm actually all positive here. If I adjust it so that this one here, this value is slightly negative. Let me just insert a negative in there and graph this again now. So it looks like our curve is completely above the x-axis, so our f double prime then is definitely going to be positive. And then actually, it never even touches the x-axis, where it looked like before was just the bottom of the screen. So there's this. The x-axis is down here. So f double prime is positive, which means f is concave up on the interval from 1 to 3. That being the case, that means a trapezoidal rule is going to overestimate the true value, because trapezoidal rules are known to overestimate on concave up intervals. On this last problem, kind of the final boss battle of this one, they ask us to write this integral as the limit of a right Riemann sum with n subintervals of equal length. So basically, all this means they want this in summation form. So we have the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I times delta x. This is just kind of one of those that you hopefully remember and write a whole bunch of times. This basically is taking the place of our integral. So where we had f of x here, we have some expression that we're going to write in here with some i's in there to kind of cycle us through all the different x values that happen between 1 and 3. instead of dx, now we're going to have an expression for this delta x. So out of all of these, delta x is generally where we like to start because this x sub I in here involves delta x. You can't really build the x sub I up without the delta x. To get the delta x, we just need to take the distance from the lower to upper limit of integration, which in this case 3 minus 1 is 2, and just divide it by n. We're basically chopping up the whole interval into a bunch of little rectangles. So that's our delta x, 3 minus 1 over n, or 2 over n. And now to get this x sub I, this is going to be the a value, the lower limit of integration, plus I times delta x. So our a value, again, was 1. To that, we're going to be adding I times 2 over n, so that's going to be 2i over n. And this whole expression, 1 plus 2i over n, this whole thing is this x sub I. So whatever this function in the integral is doing to x sub I, it's doing to all of this stuff here. So at this point, we have everything we need to actually write out our summation form. So I've got that limit of as n approaches infinity and all the rest of it. And now f of x in this case is cosine of radical x. So in this spot, I'm going to be writing cosine of the square root of all of this stuff, 1 plus 2i over n. But don't forget, you also have this delta x you have to write in. That one's a little bit nicer looking. That's just this 2 over n here. And this expression here is equivalent to this integral right here. So we're done.